Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about writing the names and chemical formulas for ionic compounds. This is the third video in a three-part series that covers naming and formulas for ionic compounds. In the first video, I talked about how you would name or write the formula for only group A elements. Then we expanded it and talked about group A and group B. And this, in the final one, we'll expand it again and talk about what happens if you have group A elements, group B elements, and you have some polyatomic ions. The three videos together should give you a really good feel for how to name these things, how to write their chemical formulas. So if you haven't watched the first two, it might be a good idea to pause and go back and take a look at them. So before we start the naming, let's talk about what a polyatomic ion is. A polyatomic ion is basically a group of atoms that are covalently bonded together, and the group collectively has a charge. Let's say we talk about the ammonium. Ammonium is NH4 and it has a positive charge. So this is a nitrogen that is bonded to a hydrogen, bonded to another hydrogen, bonded to a third one, and then bonded to a fourth one. All of these bonds are covalent bonds. They're sharing of electrons. So this nitrogen shares electrons with the hydrogen. But the group, all of these atoms together, end up with an overall charge of +1. So although the core of a polyatomic is covalently bonded, as a group, they have a charge, and so as a group, they act like an ion. Now, this is really cool because if you're talking about an ionic compound, which is usually a metal and a nonmetal, I can replace the metal or the nonmetal with a polyatomic. Let's say for a minute that we were talking about sodium chloride. Metal, nonmetal. Sodium's a +1, chloride's a -1. Well, if I look here, I've got ammonium. Ammonium is also a +1, right? Sodium is a +1. Ammonium is a +1. So if I wanted to, I could replace the sodium with the ammonium, NH4Cl. So instead of sodium chloride, I have ammonium chloride. Right? So in our ionic compounds, you can replace the metal with positive polyatomics. So that would be ammonium or hydronium. You can replace the nonmetal ion with negatively charged polyatomics. And there are a lot of negatively charged polyatomics. The majority of them are negative. So if you look through the list I have here, right, they're all negative. Now, if we do talk about the list for a minute, I have a list here of polyatomics. These would be the ones that I would consider the most popular or the ones that show up the most. If you have a table of your own, you probably include most of these, but probably not all. And I would imagine that you have a few that I don't have here. If you were to search for a table of polyatomics, it turns out that there's a lot. Some of them are more popular. You'll see them more than others, right? Some of them are pretty obscure. But this is only a partial table. All right. The other thing we should talk about before we move on, some of these have more than one name. So if we take a look at the HCO3 with the 1- charge, I can call that hydrogen carbonate, or I can call it bicarbonate. Okay, so some of these will have more than one name, and depending on where the problem comes from, sometimes the problem will use bicarbonate, sometimes the problem will use hydrogen carbonate. You'll also notice that some of them have more than one way of being written. If we talk about the acetate/ethanoate, again it has two names, polyatomic ion, you can write it as CH3COO-. Okay, so this is a group of atoms and collectively they have a -1 charge. Now, the way that we wrote this is more if you're doing organic chemistry and you would like to know how the atoms are put together. You'd like to know their structure. You'd like to know that the first carbon has 3 H's on it, that the second carbon is attached to the oxygens. But if you're not really worried about the structure, what you can do is condense everything together so that it's a little more compact, right? This has 2 carbons, so C2. It has 3 H's, so H3, and it has 2 oxygens, so O2. And it still has a -1 charge, right? That's why we have 2 different ways of writing it. Are you worried about seeing the structure, or are you just concerned with what atoms you have? So when you're looking for these things and you're writing them, you do have to be aware that sometimes they are written in slightly different forms, same atoms, just laid out a little differently, or they have more than one name. Okay. Let's talk about things that can make this confusing. Okay? You now are going to have a lot of similarly sounding ions. If you go back to part 1 and part 2 of this little series on ionic compounds, right, you'll remember that sulfide is the ion that comes from sulfur. This comes from your periodic table. This is just an element that has turned into an ion. Right, so it was sulfur. If you give it an extra 2 electrons, it becomes sulfide. So this is from your periodic table. Same thing with your chloride, right? Your chloride originally came from chlorine. Came straight from your periodic table. It was an element. We gave it an extra electron, and it did become an ion. Now for these here, where you can see that there's obviously groups of atoms, right? This is an SO3 with a 2- charge. This is an SO4 with a 2- charge. Or down here, right? You have groups of chlorines and oxygens. These are definitely your polyatomics because there is more than one atom in the group, right? So this would also be your polyatomics. But if you look at their names are very, very close, right? An S2- is a sulfide, SO3 2- is a sulfite, and an SO4 2- is a sulfate, right? They all start with the sulf beginning, but they all have different endings. You've got ide, ite, and ate. If you take a look at the next group, it's even worse, right? I've got chloride, hypochlorite, chlorite, chlorate, and perchlorate. Now, they all still have the same root word, right? They all have chlor in the middle. So chlor, 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 chlor. Some of them do have some extra suffixes, a little bit more in the beginning, hypo versus per. And the endings are different. Ide, ite, ate, and ate. So when you're doing these problems, it is very easy to read the word and then pull out the wrong formula that you're going to use, right? You have to make sure that if I ask for chlorite, that you use ClO2 1-. You got to make sure to choose the right formula to go with the right name. It is very easy to read the name and then choose the wrong formula, which is going to make your answer incorrect, right? So a lot of these are going to sound the same, and they're going to look very similar. Like if you look at this series, all we do is add 1 extra oxygen, right? No oxygens, 1 oxygen, 2 oxygens, 3 oxygens, and now you're up to 4. So the names are very close. The formulas are very close. Okay, so you have to be vigilant for that when you are naming these ionic compounds. All right. Oh, turns out I had that twice. Let's take a look at some examples. So let's say that we would like to write some chemical formulas. I've got the names written, and I'd just like to write the formulas that go with them. Now, in order to do this, I am going to need to have a periodic table because there are going to be ions here that come straight off my periodic table. I'm also going to need my table of polyatomics because there are going to be polyatomics. So you've now reached the point, let me straighten this out a little bit. You've now reached the point where your periodic table and your table of polyatomic ions are very important to your life, right? If you're going to be writing names and chemical formulas, these two are important. If you're just at the beginning of your chemistry career, then you've probably been given a periodic table and you've probably been given a polyatomic ions table. If you intend to do lots and lots and lots of chemistry, some of these things you should start to memorize, right? You'll find pretty quickly which polyatomics are the popular ones and which ones you should start to learn. And when it comes to your periodic table, same thing. You'll find that some elements get used a lot and some elements don't get used very much. And so what you really want to do is memorize the ones that show up a lot, the symbol and the name. Okay, so if we take a look at these, I would like to write the chemical formula for potassium permanganate. Okay, the potassium is an element on my periodic table. So if I take a look at my periodic table, potassium is right here. Now, I'd also suggest that you become really familiar with your periodic table and really familiar with your table of polyatomic ions. Okay, so when I say potassium, you shouldn't have to look through both the periodic table and the polyatomic ions table, right? You should know that it's on the periodic table and you should know generally where it is. If you have a friend and you both have a periodic table and you both have a polyatomic ions table, what you could do is turn it into a game. You name something, chlorate, and then your friend has to find it on their table and tell you the formula. And if you go back and forth a bunch of times, eventually you'll become quite good at finding things on both tables. Okay, that'll save you a whole lot of time later. Now, on our periodic table, if you look at video number 1, we did write the charges on top of each column. If you're in column 1A, these form ions with a positive 1 charge. If you're column 2A, they form a positive 2. If you're in column 3, you form a positive 3 ion. If you're in column 5, you form a minus 3. Column 6 is a minus 2. And column 7 is a minus 1. We do have a line here. It's called the staircase that divides the metals from the nonmetals. So these are our metals, those are our nonmetals. If you do look at the second video in the series, the one that talks about group B elements, you'll know that the group B elements, they need to have Roman numerals, right? Because like chromium can have more than one possible charge, so you'd have to have Roman numerals to tell you which one. We said that when it comes to Roman numerals, there are exceptions. Silver and zinc, although they are transition metals, don't need Roman numerals. And if you look over here, tin and lead. Tin and lead are not part of the transition metals. Transition metals are just here in the middle. But they do need Roman numerals because they can have more than one charge. Okay, so that'll make my life a little bit easier. If I find potassium, and I find that it's in group number 1, I know that as an ion, potassium is a +1. So potassium +1. Now, permanganate. If you have something that ends in ate or ite, then it is definitely coming from your polyatomics. Okay, ates and ite endings, those only show up in your polyatomic ions table. That's the only place you'll ever see them. So the minute I see that it's a permanganate, then I know that I should be looking here. And if I kind of look through it, I can see that permanganate is right here. MnO4 1 minus. So MnO4 1 minus. Now you do have to be careful. My table also has a manganite. It has the exact same formula, MnO4, but the charge is different. Instead of a 1 minus, it's a 2 minus. Right? The differences here can be really, really subtle. Okay, and the way that we usually write formulas is we'll take the charges and use them to determine the numbers. So for this one here, I have potassiums and I have permanganates. Because the charge on the permanganate is -1, I get 1 potassium. Because the charge on the potassium is 1, I get 1 permanganate. And we had said that we don't usually write 1s, so this would just be K MnO4. Potassium permanganate. And again, if you look at this, you can see that they're a perfect match. Potassium has a +1 charge, permanganate has a -1 charge, and in the world of ionic compounds, it's all about making your charges cancel. So if I've got a +1 and a -1, that's a perfect match, and therefore you only need one of each. All right, let's move on to the next one, sodium phosphate. Now, sodium is one of our favorite elements. You'll see that it shows up a lot. So when I go looking for it on my periodic table, sodium is right here, right? It's one that you're going to learn its location pretty quickly. Sodium is in group number 1, so sodium will be a 1+. Phosphate ends in 8, which means I know that it's going to be on my polyatomic ions table. So if I look down here, I have phosphite, phosphate, hydrogen phosphate, dihydrogen phosphate, right? So be careful you choose the correct one. Phosphate is this one, PO4 3-. So PO4 3-. If we do the switching thing, right, the numbers here will tell me how many of each. Okay, so if I write my sodium, I write my PO4. Because the phosphate has a charge of 3-, that's why I need 3 sodiums. The sodium has a charge of +1, so I only need 1 phosphate. And we've already said before that if you only need one of something, you don't need to write the 1. So the formula would be Na3PO4. And again, this makes sense because if I have 3 sodiums, that's a sodium 1+, that's a sodium 1+, that's a sodium 1+, and I've got 1 phosphate, 1 PO4 3-. What's the total amount of negative charge that you have? -3. What's the total amount of positive charge you have? +3. So the amount of positive charge and negative charge cancel, but you need 3 sodiums to go with your phosphate to make it happen. All right, let's move it up and try another one. Ammonium nitride. Okay, now ammonium is going to be one of those that's going to stand out for you because there's only 2 positively charged polyatomics on my table. Most tables don't even include this one. For most tables, ammonium is the only positive polyatomic ion that you're going to see. So you should recognize ammonium pretty quickly. So my ammonium is an NH4 +1. Nitride comes from nitrogen. Remember, for the elements, if you're a nonmetal, your ending changed to "ide." So the minute I see nitride, I'm thinking nitrogen. And so if I look on my periodic table, nitrogen is an N, and it has a charge of 3-. So N -3. Now, you really can't use the "ide" ending to guarantee that it's going to be a nonmetal from this part of the periodic table, because if you do look at your polyatomic ions table, there are a couple that end in "ide." Right? I've got cyanide, thiocyanide, hydroxide. Right? So there are a few things on here that do end in "ide." So the minute that you see "ide", you cannot assume that it's going to be a nonmetal from your periodic table. The chances are high because most of the things that end in "ide" will come from the nonmetals on your periodic table, but it's not 100% guaranteed. Okay, so once you've found these, we're going to take our charges and switch them to tell us how many of each one we need. So I've got NH4s and I've got Ns. Let's do the N first. Because the charge on the ammonium was +1, then I only need 1 nitrogen. So you can put the 1 there, but I'm going to get rid of it in a minute. Now, for the ammonium, because there's a charge of 3 on the nitrogen, I'm going to need 3 of them. And you can see now that we've run into a small problem that we've not experienced before. I've already got a subscript here as part of the ammonium, right? It's an NH4. But I've also got a subscript telling me that I need to have 3 of them, right? That's what the 3 here is telling me, is saying I need 3 of them. The way I've written it, it looks like there's 1 nitrogen and 43 hydrogens, right? It the 4 and the 3 blend together. So if you have to have more than one of a polyatomic, then you are going to have to use brackets. Because this tells me that I have 3 of the entire group, right? That's what my 3 is telling me. So if you have more than one of a polyatomic, then you have to use brackets, right? Because this problem is telling me that I have one NH4, I have a second NH4, and I have a third NH4. And I have one nitrogen, -3. That way I have a total of 1, 2, 3. Total of +3 and a total of -3. That way my charge is balanced. So this 3 here is telling me that I have 3 of the entire group. And so that way you don't get confused about this being like a 43. You got to use brackets. Now for this one, I really should write it again because I really don't want to write that 1 there. We don't like putting in our 1s. So this would be an NH4. You've got 3 of them. And you got 1 nitrogen. The 1 is implied. All right, let's move on to the next one. The next one is a gold 3. The minute you see Roman numerals, you should be thinking transition metals. Now we love transition metals because it tells me what the charge is supposed to be. When I write this gold is going to be a 3+. So all I need to do is find gold on my periodic table. Here's my gold. The symbol is AU. And the Roman numerals tell me that it's a 3+. When I look at the second part of this ionic compound, it says a nitrate. And whenever you see an 8, you know that it's coming from your polyatomics. So if I go looking for nitrate, nitrate is here. It's an NO3 1-. So NO3 1-. All right, let's take our charges and use them to tell us how many of each one we need. So for my gold, because the charge on a nitrate is -1, I only need 1 of them. And I'm not going to write my 1 because I know that I just have to erase it. For my NO3, because the charge on the gold is 3, that means I'm going to need 3 of them, right? This is NO3. That's where the first 3 comes from, NO3. The charge on the gold tells me I need 3 of them. That's where the other 3 comes from. And right now it looks like it's an NO33. If you have more than one of a polyatomic, you have to have brackets. Because this now is showing me that I have 1 gold 3+, right? 1 gold 3+, and I have 3 of the nitrates. So NO3 1-, NO3 1-, NO3 1-. Right, I have 3 of this group. So NO3, NO3, NO3. The total amount of negative charge is a -3. The total amount of positive charge is a +3. They balance, so this is a good formula. All right, let's see if we got another one. We got 2 more. So I'm going to do chromium 2 sulfate. Chromium 2 would be a polyatomic, it would be a transition metal. Chromium 2. The minute you see the Roman numerals, transition metals. I just have to find chromium. Chromium is here. So it's Cr. The Roman numerals tell me that the charge is a 2+. And when I see sulfate, anything that ends in 8 is a polyatomic. So I come to my polyatomics. I look up sulfate. Sulfate is right here. SO4 2-. So SO4 2-. Okay. Now this is going to bring up an issue that we saw in the earlier videos. This is a perfect pair. I've got a 2+, I've got a 2-. They match perfectly. They cancel each other out. So really for this problem here, I only need 1 chromium and I only need 1 sulfate, right? Because the chromium's a 2+, the sulfate's a 2-. Perfect match. That's what you have. But let's say that you're very much a take the charges and cross them kind of person. right? You'd like to be able to do that. So let's do that. Chromium, sulfate. Let's take the charges, cross them, and tell us how many we have. Because the sulfate's a 2-, that gives me 2 chromiums. Because the chromium is a 2+, that gives me 2 sulfates, right? 2 and 2. Now, we said in the earlier videos that you can't have 2 answers for the same problem, right? I can't say that the formula is Cr2SO4 twice and that the formula is CrSO4, right? I can't have 2 right answers. So we say that you need to reduce to lowest ratios. This is currently a 2:2, which would reduce to a 1:1. So if I rewrote this, this would be a chromium and a sulfate, 1 chromium and 1 sulfate. Now, if I insist upon putting the 1 there, then I do have to have brackets, because if I don't have a bracket, it looks like 41. But if you are going to drop the 1s, right, drop the 1s, then if there's no number out here, then you don't need the brackets. That's why I could drop the 1s and the brackets to give me this. All right, last one. Let's talk vanadium cyanide. The minute that I see that there's Roman numerals on the vanadium, I know that it is a transition metal. Vanadium is here, so that'll be a vanadium. The 3 tells me that it's a 3+. And there's cyanide. Now, it ends in "ide." Most things that I have that end in "ide" come from this part of the periodic table, but not all of them. Cyanide is one of those that comes from my polyatomic ions table, right? So if I look around, cyanide is here. And cyanide is one of those well-known enough compounds that you'll recognize its name, and so you should be able to remember, oh, cyanide? That's on my polyatomic ions table. So my cyanide is Cn minus 1. So if we rewrite our vanadium, rewrite our cyanide, and we use our charges to tell us how many of each. Because there's a 1 on the cyanide, I get 1 vanadium. Because there's a 3 on the vanadium, I get 3 cyanides. And I still have to use brackets because right now, the way I've written it, it looks like there's 1 vanadium, it looks like there's 1 carbon, and it looks like there's 3 nitrogens. Unless I put in the brackets, you don't really know that it's actually 3 of the cyanide groups, right? 3 of the carbons and 3 of the nitrogens. So even if there's no number built into the polyatomic, if you have more than 1 of them, you still need to use brackets. Now, I don't want to use the 1 on the vanadium. We tend to drop 1s, so that would be V, Cn 3 times. If you have a polyatomic, whether it ends in a subscript number or not, if you have more than 1 of them, you have to use brackets. All right, so let's say that we'd like to go the other way. Let's say that we have the chemical formula and we'd just like to write the name. Now, for these here, the issue is going to be, where do I split it? Like when I had something like sodium chloride, it was easy to recognize that the first piece was sodium and the second piece is chlorine or chloride, right? But let's say you've got this. You've got a calcium, a chromium, and an oxygen. Where do you split it to name it? Where's the first part versus the second part? Now, the biggest mistake that I see in these is that people attempt to split them up into more than 2 pieces. They would name this as a calcium, a chromium, and an oxide. For these problems here, they're all binary. Binary means they only have 2 pieces. There's a front positive piece and a back negative piece. So for these problems here, they only split into 2. You just need to split them correctly. So if I look at the first one, I've got calcium, chromium, and oxygen. I'm going to split it in 2 pieces. So my option is, do I split it so that the calcium and chromium are together, or do I split it so that the chromium and the oxygen are together, right? You got to split it. This is where your polyatomic ions table is going to come in handy. So if I look at this, I can see that there is not a single polyatomic that involves calcium and chromium. None. But if I look, I can see that there is one that talks about chromiums and oxygens. Right? If we take a look down through, right here. CrO4, right there. I've got a CrO4. This is a CrO4. So if you can find it on your polyatomic ions table, I now know where to split this. It's going to split into two pieces. The calcium is the first piece. The CrO4 is the second piece. That's probably the most difficult part of these, is just deciding how you're going to split them in half. Because if you're going to name them, Ca, that's just a single element. That comes from my periodic table. Ca is calcium. So calcium. Excellent. And we know that the name of the first element never changes. It's always the same. The second element, we just found it, is CrO4, and it's called a chromate. Chromate. Now, normally, the second piece will change its name. If you look at the first video in the series, we talked about how elements over here on the nonmetal side would change their ending to "ide." Okay, so normally the second one does change its ending, but it's only if it comes from this part of your periodic table here. If it comes from your table of polyatomic ions, here, no name change. Right? The table says that this is a chromate, and you're going to write it down as a chromate. Okay, polyatomics never change their name. The only other thing you have to worry about is, do I need Roman numerals? So if you look at calcium, calcium is here. Calcium is not a transition metal. It's not one of the exceptions. Calcium does not need Roman numerals. So that is your name. Okay, if we move on to the next one. Again, I have to decide how to split it. If I look at this, I've got a lithium, a carbon, and a nitrogen. So it's either going to be lithium and carbon together as a polyatomic, or it's going to be carbon and nitrogen together as a polyatomic. If you look through all your options, we're back to our cyanide. Where's our cyanide to? Oh, right here. Cyanide is a carbon and a nitrogen together. So when I split this one, I'm going to split it like this. Lithium will be the first piece, cyanide will be the second piece. Now, we've already said that there's very, very few positively charged polyatomics. So for the majority of these, the first part is just going to be a metal. Right? So when I split this, aluminum, first part, all of the leftovers are polyatomic. Barium hydroxide here, you split, barium's the metal, everything else is your polyatomic. This one here has gold in the front. If you split it, gold and polyatomic at the end. Okay, so for the majority of them, what you're going to find is that the metal at the front is the first piece, and then everything past that is going to be the second piece. Cation versus anion. The only place where you're going to see a polyatomic in the front is if you have ammonia. And ammonia is so unusual because it's one of the only positive ones that you should be able to recognize it. For this problem here, you should be able to say, hey, that's an NH4 at the beginning. That has to be a group. So the NH4 is the group, and the chloride is the second piece. Okay? So for splitting these, the first few, you're probably going to have to go searching your polyatomic ions table to decide, where am I going to split this? Lithium and carbon, or carbon and nitrogen? But eventually, you will start to see patterns. Right, you'll start to see that the majority of them do start with metals, and that'll be your first half, and the second half will be the collections of atoms. That'll be your polyatomics. All right, so let's name. If I look here, I have a Li at the beginning. Li is lithium, so this would be lithium. Does it need Roman numerals? Well, lithium is not a transition metal. It's not one of the exceptions, so no. If I look at the second half, I've got a C and an N together. That C and the N together have to be a polyatomic because there's more than one of them, right? There's two atoms, so it's got to be polyatomic. Poly means many. So Cn, like we said a minute ago, is cyanide. So this would be lithium cyanide. If we move on to the next one, the NH4 is something that you really should learn to recognize. If you see a chemical that starts with NH4, you have to realize that that is like the first piece, and that anything else would be the second piece. So if I look up NH4, NH4 is ammonium. Now the end of this is just the Cl. If you've got just one atom by itself, that's not polyatomic. Polyatomics are many. So if you've just got a chlorine by itself at the end, that's going to come off your periodic table. If I look up Cl, Cl is chlorine. And remember, these all change to ides. The metals don't change their names. The polyatomics don't change their names, but the nonmetals do. So instead of a chlorine, it's going to be a chloride. Okay, let's move down to the next row. So I've split these all because they all started with a metal and they all had like groups of atoms at the end. Metals tend not to be polyatomics, right? If you look through your polyatomic sheet, these are all collections of nonmetals, right? There's no metals anywhere here. So if you got a metal, it's not going to be part of the polyatomic. So all I need to do is look them up. So if I look up Al, Al is right here. It is not part of the transition metals, right? It's past the transition metal line. So it doesn't need Roman numerals. It'll just be aluminum. The second piece, now, you have to be careful here. There's two subscripts. There's an NO2, and there's three of them. Why is there three of them? Because that was to balance out the charge on the aluminum, right? If I go Al 3 plus, NO2 1 minus, where did that 3 come from? That 3 happened because the charge on the aluminum was a 3 plus, right? If we do the switch thing. So when I go looking for this thing to name it, I'm only looking for what's inside the brackets. I'm just looking for NO2. So if I go looking here for NO2, NO2. A little hard to see because I've already drawn on this so much, but an NO2, 1 minus, is right here. It is a nitrite. So this would be aluminum nitrite. Okay, if we move on to the next one. Ba is barium. It's not a transition metal, so it does not get Roman numerals. So my first word here is barium. And again, I've got an OH with a 2. The 2 outside the bracket is only there because the barium is a 2 plus, right? 2 plus told me I needed to have 2 of them. When I go looking for this thing in my polyatomic ions table, I'm just looking for the OH. So if I go looking through this, looking for an OH, right here. OH is a hydroxide. Now this is also one of those that's going to show up a lot, and you should memorize it, right? You should be able to recognize OH, hydroxide. They go together. So this would be a barium hydroxide. All right, and our last one. We got Au at the front, which is gold. We've seen gold a few times. So gold is right here. Gold is firmly a transition metal. Gold is right here in the transition metals. It's not an exception, so it does need Roman numerals. So if I do this, I'm going to write down my gold. I'm going to put in my brackets because I'm going to have to figure out my Roman numerals, but I'm going to leave it for a minute. And then I'm going to focus on the second half. The second half is the PO4. It's in brackets, so that's all I need to worry about. So if I go looking through my polyatomic ions here, I'm looking for a PO4, and it's right here. PO4 3 minus is a phosphate. So this is phosphate. Now, if you take a look at the second video in the series, the one that talks about naming ionic compounds if you've got group B elements, that's where we currently are. We now have a B element, and I need to figure out its charge. And we said basically you're going to take the little circles of the numbers thing and go backwards, right? Where did the 3 come from? Where did the 2 come from? So this was AU, this was PO4. So why do you have 2 behind the phosphate? That's because the original charge on the gold was a 2+. Why do you have a 3 on the gold? That's because the original charge on the phosphate was 3-. First one's always positive, second one's always negative. When you write down the numbers down here, though, they both become positive, right? So this is a positive 3 because you got 3 golds, but as a charge, it's a -3. So this is telling me that gold is 2+. It's got a charge of 2+. In the part 2 video, we did say, though, that sometimes this could be reduced from something like a higher ratio down, so the charges may not actually be correct. And we said you always have to check. And the way you check is you check the anion part. So does PO4 actually have a 3- charge? Yes, PO4 actually has a 3- charge, which means that your gold actually has a 2+ charge. Okay, so that's a correct name. All right, now I do have a bunch more, but let's say that we just want to try 1 or 2. Let's try this one here. If I look at it, I have a metal at the front. V is vanadium, it's a nice metal. The NO3 is actually in a bracket, so that's kind of telling you that it's all together. So if I had to split this one in half, I'd split it like that. Okay, so if we look up our V, vanadium is right here. So that's VANADIUM. Now, maybe we should pause for a minute. You have a periodic table. It's very important that when you write the names of things that you spell them correctly, okay? It shows that you're taking your time. It shows that you're being vigilant. It shows that you're committed to doing good work, right? If you write down the name of an element and you misspell it, even when the name is right here, it does show that you're not taking the work serious or that you're being a little sloppy. The other thing is, when you name these things, if we bring back this, the names of elements, the names of polyatomics, none of them have capital letters, right? Calcium chromate, no capital letters. Lithium cyanide, no capital letters. Ammonium chloride, no capital letters. If you put capital letters in the names of compounds, that's incorrect. It would be like in English if you were writing sentences and you left out capital letters at the beginning. Okay? So let's finish this one. You've got an NO3 here at the end. That is definitely a polyatomic. You just need to look it up and write down its name. So if I look for an NO3, it's a little hard to see because I've already used it a couple of times, but NO3 is here and it is a nitrate. Okay. Now, I interrupted myself talking about spelling and those sorts of issues. What I forgot to ask myself was, every time you write down your metal, you have to decide, do I need Roman numerals? And if you look at vanadium, vanadium is right here in the middle of the transition metals. If you're in the middle of the transition metals, you definitely need Roman numerals, and it's not one of the exceptions. So I am going to need Roman numerals. The easiest way to do that, take your compound apart, right? Where did this 4 come from? Now in this here, I've written on it a bit, but originally there was no number next to the vanadium. Remember, if there's no number next to the element, you assume that there is 1 because we leave out 1s. So the 1 would go this way. Why do you have 4 nitrates? Because the charge on the vanadium was 4+. Why do you have 1 vanadium? Because the charge on a nitrate was 1-. Now, before I'm willing to accept that this is the actual charge in vanadium, I have to confirm that this is the actual charge on the nitrate. So if I look at my polyatomics, again, it's a little hard to see, but nitrate is NO3 1-. It does actually have a charge of 1-. Therefore, the vanadium actually has a charge of 4+. So this would be vanadium 4. That is correct. Okay, let's move on to the next one. So for this one here, if I'm going to split it in half, I see at the front there's a CO. Now that's a lowercase o. So that lowercase o goes with the C. Do you have an element that has a symbol of CO? Yes, it is cobalt. So you do have a metal in front, which means the S and the O and the 4 all come together as a group, and that's a polyatomic. Okay, so let's name this thing. CO is cobalt. Cobalt. It is one of the transition metals, and therefore will need Roman numerals. There you go. Now, let's go look up our SO4. If I go looking for an SO4, SO4 is right here. SO4 goes with sulfate. So this is a cobalt sulfate. Now you do need to have your Roman numerals. So I'm going to take this apart. It was originally a cobalt and a sulfate that were separate. There is no number after the cobalt, which means it's automatically a 1. So that means the original charge on the sulfate was 1-, and it means that, is that 4 the number of sulfates that you have? No. Because you only had one sulfate unit, you didn't have to use brackets. That 4 is part of the formula, right? It's an SO4. So really, this should have brackets around it and a 1, because it's a cobalt with 1 sulfate. So it tells me that I have a charge of 1+. Okay, maybe we should write that again, maybe a little bigger over here. If I had COSO4, if I identify the SO4 as a sulfate, that 4 is part of the formula, right? That 4 is part of it. So really, if I want to put numbers in and say that there's 1 cobalt, then I should put the sulfate in brackets and say there's 1 of those. So when I take this apart, this 1 is what's going to go up as a charge, and this 1 is what's going to go up as a charge. Right? This 4 is part of the sulfate. You can't say I have 4 of them because you don't. The 4 is part of the sulfate. You only have 1 of the sulfate group. Okay, so now like always, we have to check to make sure everything worked out okay. Does sulfate actually have a 1- charge? No. Sulfate has a 2- charge. So for this one here, sulfate shouldn't be 1-, it should be 2-. That means this was originally reduced. It was originally not 1-to-1. It was originally a 2-to-2, right? Because the charge on a sulfate is not actually -1. It's twice as much, -2. So if its charge is -2, that means the cobalt has to be twice as much as well, so it'll be a +2. So this is going to be a cobalt 2. All right, if we look at the next example, and this will be our last one, it has exactly the same issues, right? If we talk about how many, Fe is iron, and you have 1 of them. If you look up PO4, PO4 is right here. It is a phosphate. The 4 is part of the formula. It's not telling you how many phosphates you have. It's part of its formula. So really, this should have brackets around it and a 1 to say that you have 1 iron and you have 1 of the phosphates. If we go and look up the names, iron is right here. Fe is iron. Iron is a transition metal, so it will need Roman numerals. If we look up the phosphate, we just found it, it's right here. So it is phosphate. And because the iron needs Roman numerals, we're going to do the switch thing. We need to know what was the original charge on the iron, what was the original charge on the phosphate. Because we have one of each, this one goes with the phosphate, so 1 minus. This one goes with the iron, so you have 1 plus. Now, if you look at your phosphate, phosphate is not -1, phosphate is -3. The real charge on your phosphate is 3 minus. This is another one that had a ratio that was reduced. Something got reduced down to 1 to 1. 1 to 1. So if the original charge here was 3 times as big, then that means the original charge here is also 3 times as big. Right? Because 3 to 3 would reduce to 1 to 1 here. So this would have originally been an iron 3 phosphate. Now, there are a lot of rules going on here simultaneously, right? We are finding our Roman numerals. We're trying to split things into cations and anions. We do have to worry about brackets floating around. It's one of those where it's like layers and layers and layers of things that you have to be good at. That's why I suggest that you watch this series of 3 as a series of 3. You watch the first one, which will give you the basics with the group A elements. And then you need to practice them, right? Practice writing chemical formulas, practice naming stuff. Watch the video, pause it, write your answers, and then let it play so that way you can see if your answers are correct. Then move on to the B group elements, which is the second video, and then finally move on to these. And you're probably going to have to watch it a few times to get all of the different bits and pieces because there's quite a bit. And like anything, the only way to get good at this is to practice it. You're going to have to do this many, many, many times before you become really comfortable. The reason why I say that is because writing chemical names and chemical formulas is the basis of chemistry. It's kind of like spelling in English, right? It's one of those that's a foundation skill. If you can do this well, it'll make all of the rest of your chemistry work so much better. So once again, I'd like to thank you for joining me here at Chemistry with Dr. Clark.